Okay, welcome to lesson 4. This is learning target 3. It's all about the shape of the normal distribution curve. Just to kind of recap, what we've done so far is we've really talked about how we can get a probability density graph. And if we have a probability density graph, we can actually find the area under the curve for a continuous continuous variable. So we can find the probability that a given data point lies within a specific mean or a specific interval by taking the area under the curve. We're going to revisit that in the normal distribution. The normal distribution will be a perfect example of how to actually do that. And so the question for a warm-up is, if you knew the average heights of all high school students, so say that average height was like 5'5" or 5'7" or something like that, what would be more or less likely? A very tall person or a person that's very short? So you've got and by very tall or very short, I mean like you have somebody way above the average and then somebody the same amount above the average but below the average. And then the same kind of question, a person that would be higher than the average or a person that would be lower than the average. And so that's the question here. And so if you think about it, a very tall person, a very short person, as long as you have enough high school students, like what we have is that they're just as likely. So you can have a person way above the average be just as likely as a person way below the average. And so this is what we call normally distributed. If you have a point way above, you'll have a point way below. Being higher than the average and being lower than the average, these would be the same as well. So the probability that you're above the average is the same as the probability you're below the average. What we're saying here is the middle point is actually on the average. And that's not always the case. Like, that might seem intuitive, but what we're saying here is that there's the same amount of people above the average as there are below. And it doesn't say average heights of high school students is normally distributed, and we actually don't know that for a fact, but naturally what happens, these kind of things do become distributed this way. So learning target, I know what shape the normal distribution takes and can explain some probabilities without calculating. By doing the normal distribution, we're actually going to get some intervals, and we can actually tell that the probability lies in those intervals just by knowing what shape it is. Some required definitions, some things we already know. Mean is the average of the set of the data. It's calculated by adding all the numbers, dividing by the number of data points. Standard deviation might be new. It's the distance a typical data point lies from the average, calculated as an average distance, but giving more weight to points further away from the mean. And so it really is an average, but it's calculated in a way that points above the mean more or below the mean more are worth a little bit more in the standard deviation. Okay, so it's the typical distance a data point lies from the average. So if you're right on the average, you're 0. If you're above the average, you might be plus something. If you're below the average, you might be minus something. And standard deviation is the typical distance a random point would take. We'll actually see what that means more in this lesson. And a Z-score. We're going to talk more about next lesson, but it's the number of standard deviations you are above or below the mean. We're not going to talk a lot about Z-scores today, but we'll get back to that in the next lesson. The normal distribution curve. So what we do here is we take the mass of apples, and so apples is something that's naturally produced. And so whether they're naturally produced with a bigger average or a smaller average, depending on what part of the world you're in, if we have a batch of apples, let's say the average is 150 grams and standard deviation is 20 grams. So a typical apple could be 20 away from the average. And so what the standard deviation means is it's not so much that like a typical apple, we expect an apple to lie right on the average at 150. For every apple that lies above the average, there'll be an apple below. But what we mean by standard deviation is that like within 20 of the mean, so maybe 130 to 170, most of the data is going to be there. So that's what the standard deviation means, between 130 and 170, so 20 away, most of the data is going to be there. If we take 21,000 apples, that's a lot of apples. And so that'll help us kind of get this normal curve. And we graph them on a probability density histogram. So that way we can find out the probability if we take the area of the rectangles. So we want to look at, like, if we had an interval size of 10. If we want to have an interval size of 10, this is what it would look like. We could calculate the average that we're between 130 and 170. We could calculate the probability that we're there, calculate the probability we're between 120 and 180, maybe taking half of this rectangle and the rest of these rectangles, and we get something that looks like this. Notice that there's still some like gaps here, like there's still a triangle here, a little bit here that you're over. These aren't exactly triangles, and so this here curve is actually what we want, but these guys here are actually going to be the area if we just use the rectangles. If we use an interval size of 5, like, it actually closes it down, and you can see that, like, we actually do get a little bit more accurate here. Like, your rectangles are a lot more, and like we saw in the last unit, the more rectangles we have, the more accurate we can calculate the probability. We'll give you a more accurate representation, 10 or 5. A better question is 2 or 1. If we had an interval size of 2, we've got this kind of thing, so we've got the rectangles. And the red is actually what we're expecting. The red is an interval size, or we'll see that in a second. If we have an interval size of 1, we got even more accurate. Like, we're calculating the average or the area of all these rectangles. The rectangles become very precise. Eventually, we get the normal curve, and this is the curve that came up throughout. The red curve that came up before, and this is actually the perfectly distributed one. That's an interval size of very, very, very small as we can get. And you can see as we close the interval more and more, we actually get closer and closer to that red curve so that we can accurately represent this. When we actually use this curve, we're going to use a chart that has an interval size of 0.01, and so the rectangles are going to be 0.01 apart, and so that way we can really calculate this very closely. And just really so that we can take the average or the area under the curve. And so this is what we get as the smooth normal distribution curve. And you can see, like we were saying, the probability that you're really high is kind of like the same as the probability of being really, really low. The probability of being above the average is the same as being below the average. Okay. A couple things about it. It is symmetric about the average. The median's in the middle. So the median and the middle are the same. So the middle number is right in the mean. And this is the key here. Approximately 68% of the data, this actually we want to memorize. 68% of the data lies between 130 and 170. That's the definition of standard deviation. When I say majority, it's over 2/3. 68% lies between 130 and 170 as a weight of an apple. 95% is another standard deviation. So if we go 20 more in both directions, 95% of the data lies between there. So if we go 110 to 190, we can actually see that covers about 95%. And then 99.7% go from 90, so that's 3 standard deviations away from the average, to 210, which is another 3 standard deviations. So 6 standard deviations in total, or from 90 to 210. Z-score is further explained. So we said that this is Z-score is the number of standard deviations. Just looking at what a Z-score is. If we had a mass of 130, the Z-score would be -1 because we're 1 standard deviation below. if we had a mass of 170, the standard deviation would be 20 above, which is plus 1. Sorry, I didn't fill these in. Standard deviation is a z-score of 0 would actually be right at a mass, like that would be, you're not above or below the mean, that's a mass of 150. And a mass of 100, if we look at, like starting at 150, if 130 is negative 1, 110 is negative 2, 100 would be negative 2.5. Okay? This is a big slide. This is important. So we see here z-score of 0 is the mean. Z-score between negative 1 and 1 is 68%. And so this is for any kind, like not just apples. If we have any average and any standard deviation, we can convert it to z-scores. From negative 2 to 2 is 95, and from negative 3 to 3 is 99.7. And you can see that it's really almost all of the data between negative 3 and 3, 95% of the data between negative 2 and 2, and 68 between negative 1 and 1. The reason why we use z-scores is so that we can talk about things not just in terms of like mass and mean and standard deviation, but just in general, because this normal curve doesn't just happen for apples. It happens for heights of people. It happens for anything that occurs naturally. Although all standard deviations share the same previous probabilities, the shape can change drastically depending on the size of the standard deviation. So if you have a larger standard deviation, it's just more spread out. If you have a smaller standard deviation, 68% of the data is a lot closer together. Okay, it's important to kind of note that, like, you could, like, the shape could depend on the standard deviation. This notation I don't really assess you on, but if you're going to move on in math, you might see this in stats in first year. We call x bar the average and sigma the standard deviation. And so what they write here is sigma squared, which is called the variance. So if you see that x, which we talked about is a random variable, we say it's approximately normally distributed. That's what these words mean. I wouldn't worry too much about this. Drawing the probabilities, suppose the time before burnout for a light bulb averages 50 months with a standard deviation of 5 months and is approximately normally distributed. We always say that. And so this is something that happens naturally. So things happen hot. Like, you could have a light bulb that lasts a long time or a light bulb that lasts very little time. So draw a diagram that lasts longer than 55 months. And so what this would look like, between 40 and 60 and less than 38. So longer than 55, it looks basically like this. We do a little dash at every standard deviation. We've got a 5-month standard deviation. So longer than 55 is the area under the curve here. So that it looks like this. And it's kind of misleading that it stops there. It just keeps on going forever there. Between 40 and 60, there's a dash at 40 or a dash at each standard deviation just to kind of represent the z-score. And between 40 and 60 is what we actually like. That's your 95% lying there. And less than 38, 38's not right on a standard deviation number. This is something that we're going to have to learn how to interpret. We haven't learned yet. So it's not one of the numbers that come up, 68, 95, 99.7. But just to color it in, it's everything less than 38. This is the area that we have to calculate here to find out the probability. This guy here is interesting. Like, if 68% of the data lie in here, then 1 minus 68% would lie in the entire thing. So in other words, like 32% would lie on the outsides. And so this guy here would be half of that. So we can calculate this actually with just knowing the 68, 95, 99.7. This is 16%. That's one of the skills that I'm going to want you to be able to do for a mastery learning target. Calculate as many probability intervals as you can. So this is the greater than 55. We could also say less than 45 is 16% as well. Between 40 and 60 is 68%. And we could say less than 40, again, you can see is 16, and this is 16. Greater than 55. Sorry, this is 95%. 40 to 60 is 95%. It's 2 standard deviations away. So this is 2.5% is less than 40. This is 2.5% greater than 60 because it's 95. They all have to add up to 100. So if you can just kind of estimate this is just less than 2.5%, maybe, because 40 would be 2.5. This is maybe 2% chance of less than 38. So just by knowing this curve and knowing some of the properties, we can tell a lot about the probability just by estimating. Some discussion questions that goes along with massive apples that has been a mean of 150, standard deviation of 20. Estimate the probability that a random apple is between 140 and 160. So remember 130 and 170 is 68. So what would 140 and 160 be? You could draw it and estimate. For the mass apples, what is a question that is easier to estimate than the range above? So this is a little bit harder to estimate. So we can think about like right on Z-scores being easier. For the mass apples, what are the Z-scores used in number 1 and number 2? So you can kind of see what these are versus the standard deviations. So how many standard deviations are you below and above? And then this one is a little bit easier. So you can use right on Z-scores. And we already talked about like this, or what are the probabilities for each of the drawings used in slide 10. So you can kind of go back to these and make sure you understand what the probabilities are. Okay. Some questions there to practice from the textbook and a mastery question. So this is what the mastery question will basically look like. Using the shape of the normal curve, I really want you to understand as many of these intervals as you can. And 3 of them are given when you're at exact standard deviations. And so using those 3 numbers, 68, 95, 99.7, want to predict as many probabilities as you can that don't use the mean. So like if we say we use the mean, all I mean there is like obviously you know like 0 to 1 is 34. You know that 0 to greater than 0 is 50. Less than 0 is 50. So I'm asking you to not use the mean. So not just cut these in half, but think about maybe between +1 and +2. You've got 3 here. That gets you started. What about between +1 and +2? What about between -3 and +2? What about between negative or greater than -2? So those are all good intervals to kind of think through. On the actual mastery question, I'll tell you how many intervals to do. And we're looking probably in the range of 7 or more intervals to come up with, just so that you really understand this shape. Okay, that's it.